Okay, we're well and truly on the downhill now. Here is part H. It says, from parts F and G, it follows that, and then you've got this inequality result here. Now, read carefully, because I know the first time I had a look at this, I thought, oh, okay, so I've got to prove this result. And then I read it again, and I said, oh, no, they're just telling you this. They're giving you a corollary, a sort of consequent that you can draw out of parts F and G, which we just proved. They're just handing this to you, okay? And if you want, you can go back to F and G and see how this inequality arrives. What they want you to do is use this result, take it as given, and then add it with this substitution, x equals pi on 2 sine t. So let's just highlight that there. They want us to use that, and then this is the thing we actually have to establish. This is the result I'm required to prove. Bn is less than or equal to this, which is less than or equal to this. So, there's a lot going on here, right? There's this sort of multi-part inequality, which is, in a sense, just two inequality questions rammed into one, and you just want to do them independently, and then you link them, right, using that common piece in the middle. You can see, if you look carefully, that there's a relationship between this result that they've told you comes from F and G, and then this result which you're required to prove, right? Have a look. You got Bn over here on the left-hand side, and then you've got this series of very similar looking things, right? You've got this same old integral from 0 to pi on 2, there it is. The coefficient, the constant coefficient that's been removed out is very suspiciously similar. Not identical, but you've got, what color have I got left? I'll use this red. You've got pi squared up here, so there's like a pi cubed, so it's a pi squared and somehow another pi arrives. You've got that same n plus 1 hanging out there on the denominator, and then you can see the 8 is somehow going to turn into a 16. So in fact, what we're off by is a factor of pi on 2, right? Can you see that if I multiply this by pi on 2, you get to this, and that should make you very suspicious of the pi on 2 that appears in this substitution they've asked us to work with. So here's going to be my roadmap. What I'm going to do is I'm going to start with this result over here. I'm going to try and manipulate it using this substitution, and I hope it will land me here. Slightly weird that there are sines and I should end up on cosines, but it wouldn't be the first time, even in this question, that we've just kind of treated them as somewhat interchangeable and made an exchange between them using the appropriate identity. Alright, so that's the roadmap. Let's have a go. I'm going to start by writing the substitution they've handed us, right? Which is x equals pi on 2 sine t. Alright. From here, I'm going to do all the normal things that I need to in order to make a substitution. You can see up here, I'm going to have to change some boundaries. I'm going to have to, change my variable of integration. And there's also this x squared term here. I want to deal with that and make sure I've got all the right pieces in terms of t. Okay, so let's have a go. What did I say before? We're going to have to do boundaries, change the variable of integration. Let's start with boundaries, okay? So over here, let's just draw a line over here. Okay, boundaries, here we come. So previously I had x equals 0 and x equals pi on 2. So when I substitute that in, what's t going to give me? Well, I'm going to have, think about this, right? Not t equals, I'm going to have 0 equals pi on 2 sine t. Well, divide through by pi on 2, it doesn't matter. What value of t is going to be appropriate to give me 0 on the left-hand side? And the answer is, well, t equals 0 will do it, right? Now, of course, t equals 0 is not the only value that is necessary, but if you have a think about what you're dealing with here, it's an appropriate place to start, and it's going to be an appropriate place to end. So I'm going to set that as the most appropriate solution to give me a reasonable value. So that's going to be t equals 0. Kind of cute, funny thing happens when you substitute in x equals pi on 2, because then what you've got is pi on 2 equals pi on 2 sine t. So you're like, oh, okay, I guess I'll just divide through. That gives me sine t equals 1. So again, choosing the most appropriate value, the first one that's going to give us a satisfactory solution is pi on 2. So funnily enough, our x equals 0 becomes t equals 0, and our x equals pi on 2 becomes t equals pi on 2. So weird, all right? Let's keep on going. Let's have a look at changing the variable of integration. So I need to work out what, looking at this, I need to work out what dx on dt is here. Pi on 2 is just a constant coefficient. Sine is just going to turn into cos. So let's just jot that down. Dx on dt, it's going to be pi on 2 cos t. t. All right, fantastic. And then you actually have to look at the integrand itself. So when you have a look, see here, we've dealt with the boundaries, we've dealt with the variable of integration. What is this thing going to be equal to? Now I could substitute in x equals pi on 2 sine t alongside doing the integration at the same time, but I'm just trying to reduce my cognitive load and have as few things going on in my brain simultaneously as I can. So I'm just going to work out what 4x squared on pi squared is in terms of this, and then I'm going to substitute it all in one here. Okay, so when I go down over to this direction, let's say if x is pi on 2 sine t, then x squared is going to be pi squared on 4 sine squared t. I think I squared everything okay. And then what I'm going to do is I want 4 on pi squared, which looks a bit suspicious, doesn't it? I'm multiplying through by the reciprocal of this coefficient. So therefore, when I multiply through by 4 on pi squared, on the right hand side you just end up with sine squared t. That looks like it's going to be useful. Okay, so I'm ready to go. Let's go ahead and change let's just do our substitution, okay? So originally we had our integral from 0 to pi on 2. Because I'm doing a change of variable, and because it just so happens that my boundaries are actually the same, I'm going to be very explicit. You guys have seen in sigma notation, they state for you what the pronumeral, sort of the dummy variable is down the bottom, and in sort of calculus integral notation, we tend to drop that off. But just because I'm changing this, I think it's a good thing to actually say. So that's there. And then what I've got is, what do we have? 1 minus 4x squared on pi squared. It's all raised to the power of n plus 1. That's with respect to x. Okay, here we go. Time to make our substitutions. I'm going to go from t equals 0 to t equals pi on 2. So that looks good. Inside the brackets here, you can see I'm going to get 1 minus, and I went and found that that is just going to be sine squared. That's handy. So 1 minus sine squared t. And then when I'm doing my substitution here at the end here to change my variable of integration, you can see that dx I can replace with a pi on 2 cos t dt. So I will pop that in green since that's what I was doing over there. So this is pi on 2 cos t dt, and I'll just, for completeness sake, I'll highlight this in blue because you can see where I got that from. Okay, happy times. So now on the right hand side you can see, oh, this is going to have that pi on 2 is going to come out the front like I wanted. That's going to multiply through like I identified just here, so you change that coefficient that's out the front. Okay, so that's promising. I'm going to say, oopsie daisy, this is from 0 to pi on 2. I'll drop off the t now because I think it's obvious what I've done. And oh, that was a bit sneaky of me, wasn't it? I forgot to raise this to the appropriate power, which is n plus 1. This is cos squared t to the power of n plus 1, right? So cos squared to the power of n plus 1. But then you've got, check this out, another cos, right? So you can see now why the power in this middle term here, it's like, oh, 2n plus 3, where did that come from? Answer, this is going to give you 2n plus 2, and this is going to be the increment up to plus 3, okay? And then that's all with respect to t. Okay, fantastic. Now we can say this is equal to pi on 2, 0 to pi on 2, let's just do that expansion there, cos of 2n plus 3 of t dt. Okay, excellent. Now this is so important because it's kind of this result that I'm going to need to put into here. I'm going to name it, okay? So I'm going to call this equation 1, right? And you can see where it's come from. So as soon as I get this, oopsie daisy, let's try that again. Missed the top of the pie, you don't want to do that. So let's grab that. As soon as I see this result here, whoops, so uncoordinated, just because I've been doing so much writing. There we go. As soon as I receive something to do with this, I can substitute it for this, and that's going to give me the result that I need with this sort of linked inequality, okay? So I can say, given the, in the question, do you remember, f and g tell me this, right? Remember that? And then what you've got here on the right-hand side is the thing I'm going to substitute for this cos 2n plus 3 business, okay? So what I'm going to say is, since bn is less than or equal to, there's the pi squared on 8n plus 1, then's the integral from 0 to pi onto, in fact, I think I have everything up here, like so. Right? Where did that come from? Answer, it was given to me in this particular question, so I'll just say given. I'm now going to do this substitution, right? So I hope you can see that I'm going to substitute, let's highlight it, let's do screen. I'm going to highlight this here. Let's fill that in. Ta-da. I'm going to substitute that for being that it's the same as this result over here. I'm going to substitute it for this cos to the 2n plus 3t dt, okay? And that's going to go in place here, and the inequality will be preserved because these two things are equal after all, okay? So what that's going to give me is bn is less than or equal to pi squared on 8n plus 1, and then comes everything that I did here, right? You see that? That's me doing that substitution. So I'm going to say that it's all multiplied. And I'm getting that by substituting 1. So that's where I got that result from. Okay, and from here you're like, oh great, the sort of pi cubed is going to appear, the 16 is going to appear. So I've got, you know, sort of 2 of the bits of the 3-part inequality that I want, right? So I've got bn is less than or equal to, all right, pi cubed on 16n plus 1. And then everything in this integral is looking good. Okay, so fantastic. This is happy. I'm going to refer back to this shortly, so you can say, okay, I've got this result here. I'm just going to call this 2, and I'm going to substitute it back in a second. Now, we had this linked inequality, right? I said it's really 2 inequality questions balled into one, right? So being that I've dealt with, let's have a look here. I actually might delete all this other working here now because we've done this part, so I can say that. We are now going to focus on this side here, right? So you're like, what's happening? Well, in the first instance, what I can say is, look, the pi cubed on 16n plus 1 is the same here and here. So I'm actually just going to momentarily disregard it, okay? Then you've just got this integral in here, and an comes back, right? I haven't dealt with that for a while. What is an again? Well, if you have a think about, if it's still kicking around in your memory, it's the integral from 0 to pi on 2 of cos to the 2n t dt. Okay, or rather it's actually all in terms of x's, but it's a dummy variable, right? So t dt, x dx, theta d theta, it's all the same, okay? And what I want to do is compare. You can see we've already noticed that the constant coefficient's identical, the boundaries are identical. Really all the action is happening in here, right? This is what's different to this, right? We're saying that apparently this result will always be less than or equal to this result. How does that work? Well, remember that integrals can be interpreted as areas under a curve. So if we're thinking about this as areas under a curve, why would it be, like what's the actual difference between this term and this term, which is apparently less than or equal to? And the answer is, to get from here to here, you're multiplying by cos t, and you're doing it 3 times. That's what gives you this plus 3 here, right? The thing is, in this particular domain, from 0 to pi on 2, cos t is always between 0 and 1, right? So when you multiply, you know, if you have some number, n, right? You multiply it by some other number, which I'm telling you is between 0 and 1, the biggest it can be is the original size. If you multiply by 1, you just get back n. But any of the other options, you're going to get something smaller, right? And if you did repeated this process 3 times to do the plus 3, you'll get smaller and smaller and smaller, or at the best case scenario, you stay equal to the same size. And that's exactly what this inequality sign means, right? You'll be smaller or you'll be equal. That's what happens when you multiply through by cos 3 times successively. So how do I reason that? What I would say is, I'm going to say that cos t is going to be between 0 and 1 for this particular domain, right? From t to pi on 2, right? Therefore, the area under a curve will be lower on successive multiples of, or successive multiplications of cos t, because you're multiplying by something that can either be the same size or smaller, right? So I'm going to say of cos t, right? So therefore, what that tells me is that this over here, I can duplicate that, that is going to be less than or equal to the same thing, but you know, before you multiplied it by cos t 3 times. So that's all of this, and I'm just not going to have the plus 3 right there. Okay, so this here is what I've just reasoned through, and obviously it's critical that you actually say, you provide some rationale, some substantiation for your claim. And what you've got here is on the right hand side, look at this, this is an, like I was pointing out before. So I can just kind of make that substitution, right? I can say i.e. all of this is unchanged, but what you're substituting on that right hand side is an, okay? And so that was it. Like the previous one took so much more work, but here all I have to do is to attach this middle term to the one on the outside, and then I can have three terms, one small, bigger than the other, bigger than the other. Okay, so I'm going to say that linking with inequality, I'm pretty sure I called it inequality 2. Let's just go back up there and check. 2. There it is right there. So in fact, I'm just going to grab that right there. There is the left-hand part of it, right? And if you just follow the logic from this previous line, that is subsequently less than or equal to that. And that's it. That is the result that we were required to prove. Okay, fantastic. All right.